In this video, we're going to look at some examples of applying VSEPR theory in order to predict molecular structure. So we've introduced VSEPR theory and talked about how lone pairs are accounted for in VSEPR theory geometries. So now I just want to take two examples and look at how we can use VSEPR theory to predict molecular structure in these examples. So in the first example, we have ClO3+, so there's the chlorate cation, and Br3- ion. So let's look at the first example of ClO3+. So obviously the first thing that you want to do is to construct the Lewis structure for your molecule. So we have ClO3+, so the first thing we want to do is consider how many valence electrons we need to represent this structure. Right, so we know that chlorine has a characteristic valence of 7, right? So we got 7 from chlorine. Plus, oxygen has a characteristic valence of 6. There are 3 of these guys, so we'll have 6 times 3. That accounts for the 3 oxygens. Now, since we have a positive charge, that means we're going to have 1 less electron than we have protons, right? So that's going to be a -1 off of these characteristic valences. And so when you add all of this stuff up, you get 24 valence electrons total. Okay, cool. All right, so let's bond all of the atoms. So connect the atoms. So in this case, we know that chlorine will be the central atom since it's only one of those, and all of the oxygens should be attached to the chlorine. So if we connect the atoms in that way, then we get this guy. So we got chlorine, 1 oxygen there, 1 oxygen there, and 1 oxygen there. Okay. So in order to fill this Lewis structure, what we're going to do is double bond to 2 of these oxygens, add in lone pairs there, and for the last oxygen, just fill in lone pairs here. Now, whenever you have an overall charge, whenever you have an ion, you can actually utilize formal charges in order to confirm that you have the proper connectivity in your Lewis structure. If the sum of your formal charges does not add up to the overall molecular charge, then you've done something wrong. So we want to calculate formal charges here and make sure we've done everything right. So for chlorine, formal charge will have a characteristic valence of 7 for chlorine, minus, we don't have any lone pairs around the chlorine, so we'll put 0 there. Plus, we got 5 bonds, 2 here, 1 there. So we got 5 bonds. So that's going to give us a charge on a formal charge on the chlorine of +2. And we got oxygens that are in 2 different environments. We got this double bonded oxygens here and a single bonded oxygen. So first we'll do the formal charge for the double bonded oxygen. So you got a characteristic valence of 6 for oxygen, and you got 4 lone electrons, so we'll get 4 lone dots, and we got 2 bonds, 2 dashes. So that's going to give us a formal charge of 0 on all of these, or on the double bonded oxygens, on both of those. And then for the single bonded oxygen, again, we have a characteristic valence of 6 for oxygen, minus, we got 6 lone pair electrons, plus 1 bond. That's going to give us a -1. So let me denote these formal charges on the structure. So for chlorine, we're going to have +2. For all of the oxygens, we have 0s. And for the single bonded oxygen, we have -1. Now, if you add up all the charges, not an absolute sum like we were doing with the determining the most stable structure with formal charges, if you take an actual sum, so 2 minus 1 is going to give you a +1 overall charge for this molecule. So that confirms that we have made a correct structure here because we have all of the atoms connected. Octets are full for oxygen. Chlorine's fine with an expanded octet since it's below period 3. And we have the correct charge here. So we have a correct Lewis structure for ClO3. Now we have to do our VSEPR theory, have to go through our VSEPR theory steps. So first we're going to have to calculate the steric number. So we're going to calculate the steric number. steric number for the central chlorine, we're going to have 3 bonded atoms, right? So we have one oxygen here, one here, right? So 3 bonded atoms. Plus, we got no lone pairs around this chlorine. So we're going to put a 0 there. So that's going to be a steric number of 3 with no lone pairs. So I've got our VSEPR theory chart here. And if we have a steric number of 3 with no lone pairs, then that means that we have a trigonal planar shape predicted by VSEPR theory, right? So if we were to draw out this ClO3 plus ion, then it would look like this. Right, so this would be the VSEPR theory geometry that would be predicted for this ion, right? And again, I just like to put the overall charge up here. So we got +1, or usually with +1 or -1, we usually just put plus or minus. Okay, so this would be the predicted 3-dimensional geometry for the ClO3 plus ion. This will be trigonal planar. And so first, always start with a valid Lewis structure. So if I did not do this Lewis structure correctly, I would not be able to get a correct prediction of the 3-dimensional structure. So starting with the Lewis structure is key. Checking your charges if you have an ion is useful. And then from there, calculate your steric number and then figure out what is going to be your overall 3-dimensional shape. Okay, so let's go to the next one, the Br3 minus ion. So again here, how many valence electrons do we have? Right, so bromine is going to have 7 valence electrons, right? And we got 3 of these guys. So this actually accounts for the entire molecular structure. And we have a negative charge, which means we have more than one electron than we have protons. So that's going to be +1. So that's going to give us a total of 42 valence electrons. 42 valence. Okay, so for 22 valence. Sorry, my math there. 22 valence. Right, because 7 times 3, 21, plus 1 is 22. That's how you math. Okay, so 22 valence electrons there for bromine. Before Br3 minus. So now we want to just connect everybody. So we're going to connect bromine to bromine to bromine. But in doing so, we've only accounted for 4 valence electrons total. So we got 18 that are left to account for. So what I'm going to do is fill the octets of these guys on the sides. And now, because bromine is below period 3, again, it can actually readily accept more than an octet of electrons. So we're actually going to have this central bromine be an expanded octet. Right? So doing this actually gives us a correct Lewis structure for Br3 minus. And I'll leave it to you, viewer here, to calculate the formal charges and confirm that this would give you a correct representation of Br3 minus. Okay, so we have this representation of Br3 minus, and if you weren't counting lone pairs, then you might just think, oh, this is a linear molecule because it's got 2 attachments. Well, that's why we calculate the steric number, right? So we want to calculate the steric number here. For Br3 minus, this central bromine is what we're going to be keying in on. And we have 2 atoms bonded to this bromine, plus we have 3 lone pairs. So that's going to give us a steric number of 5 for Br3 minus. Going back to our chart, if we have a steric number of 5 with 3 lone pairs, that actually gives us this linear structure. So we do end up with a linear structure, but not for the reason of just having 2 attachments, right? So these lone pairs are actually going to form kind of a trigonal planar base. So let's show what that looks like. So we're going to have 1 here, right? 1 lone pair there. And then we'll have one here, one going into and out of the board. So those kind of form like a trigonal planar base, right? And then you have your linear bromines on top and bottom, right? So we'll put our lone pair electrons there, right? And so this gives you a linear structure where all of the lone pair electrons are pushing those bonded atoms into a linear structure, right? In order to minimize electron repulsion. So this guy is going to be linear, right? And so we can kind of go to the chart here again, just for probably a better drawing of that, right? So these lone pairs form that trigonal planar kind of base, and then the bonded atoms are going to be in this linear fashion, right? Okay, so those are two examples that I wanted to go through. So just kind of applying VSEPR theory to predict molecular structure in these two cases.